All right. Hello, everybody. Good morning, good afternoon, good evening, whatever time of day you are deciding to watch these videos. Um, so this is actually a little bit of an addition from the videos that are already available for you. Just of like how things left off in terms of material that we were able to get through in our last class. So if you're watching this video for spring 2024, there was just a little bit that we didn't get to in class. So that's what we're going to start with today. So what we ended with in class together is talking about surface circulations. And we observed that there's basically 5 main gyres, or overall large circular circulations at the surface of our oceans. And there's a consequence to those circulations, and it's something that we can observe in the oceans, and it's something that is 100% of human consequence. And perhaps you might be familiar with it, as it's been talked about a lot, I think, especially in social media, and that is the Great Pacific Garbage Patch. So whenever I was taught about the Great Pacific Garbage Patch, or if I heard that term, I would always automatically go to like thinking about it in a sense like these pictures have it make it seem, where you have all of this floating garbage. You can clearly see it from a top-down view. If you were to actually be in the water, you could see all this debris and stuff kind of floating around, when in fact, a lot of the Pacific Garbage Patch, you can't actually see the debris in the water from high up. And this is why we can't see it via satellite, right? So it's not like these big, super large chunks of plastic. They actually get broken down into what we call microplastics. So basically what happens with a lot of plastic, it's amazing, right? It's cheap, it's durable. We use it in pretty much everything, but it breaks down eventually, right? So say this is like my smoothie breakfast shaker thingy. If I were to just leave this out in the sun for a long time, the plastic would get more brittle, right? It's taking in all that sun energy, it's kind of breaking the plastics down, and then it'd be much easier to break. And so you add that element on top of being on the water, which can be tumultuous. You have waves breaking. You have animals perhaps that are coming over and kind of pecking at whatever they think this is, and it breaks these plastics down. So it's not like these macro large plastics. It's these really, really teeny tiny plastics. So that's why we can't see it at the surface. It doesn't mean that there's not larger plastics in the oceans. There most certainly is, but the majority of the mass of these large patches tends to consist of microplastics. So unfortunately, because of the reality of these garbage patches, of it being microplastics, right, it's really difficult to just go and clean it up. It's really much more effective to confront the plastic when we encounter it in our lives before it reaches the ocean. But of course, there are folks out there who are trying to make the world a better and cleaner place. And this group in particular is called the Ocean Cleanup. Perhaps you've heard of them. It's basically like the science fair experiment of this kid. His name Boylan Slat out of Denmark, I believe Denmark, but they basically came up with this idea. People funded it. It's a complete nonprofit organization, and his goal is to go out of business, right? He wants to be able to clean up the oceans enough that they no longer need to be of service. So what this diagram here on the right basically shows what they're doing in the patches themselves. So there's 2 boats kind of on either side, and they've really, really, really slowly moved together through the water, and they have like little nets that collect the debris it's basically like skimming the top, right? And then they extract it, and then they take those plastics and they analyze them, see what it's made out of, where did it come from perhaps, if there's like a name or a date or whatever on the plastic itself, it makes it easier to kind of backtrack where it came from. And then they end up recycling what they can. And you can buy products from them that are made out of the recycled materials. They're obnoxiously expensive, so I'm not going to suggest doing that unless you are rich. Then go for it. But so that's how they do it in the garbage patch itself. They also have something called the Interceptor, which is this cool little ship that like collects trash at the river systems straight before they go into the oceans. So they have these deployed in some of the most polluted or polluting cities that they've been able to work with local governments to allow them to do that. I know there's one in Kuala Lumpur, Malaysia. I think there's one in Bangkok, Thailand. I think there's even one in Los Angeles, California. So doing something like that, I think, is a bit more beneficial than this, though I think we should obviously be doing both, right? Obviously be doing both, but I like that they're trying to encounter this problem on both sides. So something also to consider with plastic pollution, it ends up in the ocean from inland regions, right? And many sources estimate the amount of time that it takes for plastic to degrade is going to be a really, really, really long time, right? Like thousands of years. But scientists are still unsure because of lack of direct observations. We have not been here for long enough. Humans have not been around for the same length of time as plastics to really see how long it takes for it to break down fully. So kind of wild. So do your part, right? Throw everything you can in the trash. Don't litter. Don't throw your cigarette butts out into the streets. Yell at people that do that kindly, not to some stranger, but, to reduce your impact. So those are some impacts of circulations. There's some consequences, I guess I should say, of the gyres and what we see collecting within that. The last thing I want to mention and go into and explain is a different sort of concept in terms of circulation called upwelling and downwelling. Hopefully this isn't a new concept. We covered upwelling when we talked about El Nino and La Nina. It's a very important process off the coast of South America, right, if you recall. But the whole main take-home point of upwelling and downwelling is to really understand that we're talking about the continuity of flow and the conservation of mass. So if you're taking water away from somewhere, it has to be replaced with something else. And essentially that's what's happening. So if you recall the process of Ekman transport, right, you have this overall net transport of the water 90 degrees to the right of the direction of the wind. So you're taking that water away, but that water is being replaced from the deep oceans. In terms of upwelling. So upwelling is really important for delivering nutrients to places, and downwelling helps oxygenate deep ocean water. So both of these kind of play into effect all over the place, which is kind of cool. What we're concerned about here, especially in California, is coastal upwelling. And not concerned to be like, oh no, but concerned like this is a very important process for us. So we have surface water divergence, which helps enable cold, nutrient-rich, oxygen-deprived waters to rise up to the surface. So this nicely reintroduces this idea of Ekman transport. So if you have your winds coming down the coastline, your Ekman flow or Ekman transport would be away from the coast, and upwelling would occur to replace the water that's being sort of taken away. And the reason that this is important, and if we look at coastal upwelling zones, it really only makes up about 1% of ocean environments, but these upwelling zones support a very, very rich and very, very important ecosystem that's right in our backyard. Give this video a pause and think about which ecosystem I might mention in the next slide. Think about it. And if you thought kelp forests, you were super, super right. So kelp forests often occur in association with upwelling zones. They're super productive marine habitats. Productive meaning there's a lot of life that's happening, starting really at the base of plants, kelp being that base. So kelp forests line all of California up and down the coastline, and they support vast amounts of species. I think we've talked about this a little bit before when we talked about the sea otter, kelp, and sea urchin relationship, right? And making sure everybody stays in check. This picture here is of a lovely sheephead wrasse they also play a very important role in keeping urchin in check because they are a bigger fish that can help with those spiny little critters. Then with downwelling, it's basically the opposite, right? So you have convergence of water coming together, and we don't have the physics on our planet, don't have, fountains of water just popping up all over the place where you would have this convergence, this coming together of water, generally due to wind directions, right? So because of that, that water is then churned downwards or is forced down the water column as opposed to like flying out into the water, creating a fountain. And here's an example of what that flow would look like if the winds were coming from the south. You would have Ekman flow going towards the coast, and then that would force the water underneath that flow and just allow for this continuous motion. So all of these things combined, considering temperature and density and circulation and movement, upwelling and downwelling, all this kind of stuff really brings us into this idea of the layered oceans. So this is a kind of a slice, if you will, of the Atlantic Ocean, going from sort of Greenland-ish all the way down to Antarctica. And what I want you to pay attention to here in the various different layers of the oceans are the temperatures that are involved, as well as the various salinity. PSU, the practical salinity units, are parts per thousand, which is what this little symbol looks like, that percentage that looks like that little extra doohickey on the bottom. And kind of how things move around in the depths as well as at the surface. We have surface convergence zones and surface divergence zones. So those would be areas of relative upwelling or downwelling, which will be covered again in the next video or so. Then going back now we're going to transition into smaller, much smaller circulations that we observe on the ocean surface. But here's just a brief review of our surface currents, right? Our 5 main gyres, but we can't forget about our Antarctic circumpolar circulation or circumpolar current. But if you recall, or what you can even see here, are these sort of smaller little circulations that don't fit into these main 5 gyres. And if we were to look even a bit closer, we could see even smaller circulations, right? And I know I prefaced at the beginning of this unit that scientists are still trying to understand all the motion in the ocean and really figure out why a lot of these much smaller circulations occur. And they've been able to identify some of them. And we will start here talking about eddies. So eddies are really cool. They're these little pockets of moving water in a circular pattern. They take with them the energy of motion from the main flow and allow it to gradually dissipate this energy through friction, right? Friction is a big player here in ocean movement. Not as much really in atmospheric movement, but certainly in or at least in the upper atmosphere, but in the oceans. This helps kind of mix and blend water. A really beautiful example of this is the Gulf Stream. So what we tend to see, you have our full-on Gulf current. This is the Carolinas, I think North Carolina here. And so you see this really nice overall stream. And on either side of those streams, you can see these little miniature circulations and sometimes pockets of warmer water where it would generally be cooler, and pockets of cooler water in generally warmer water. It's really quite fascinating. And so on the bottom of this diagram is trying to show like how we think this process occurs, right? You have your main flow, and then you have a counter flow on the other side of that. And because you have this sort of counter motion, it allows for these other little circulations to occur. Another way that you can kind of think about this, or an analogy that you could use, if you've ever been canoeing, or if you ever have stirred a cup of coffee, or put your hands through water, like say you're swimming in a swimming pool or in a hot tub or something, and when you put put whatever you're using through that fluid, you can see all these little circulations that occur on either side, like these little vortices. That's kind of how you can think of eddies. And it's really quite an interesting and fascinating concept. So here are a couple of examples. This is on the left, we're looking at the Gulf Stream and sea surface temperatures. So you can see where the initial main current is, and then you can see these little pockets of warm, like this little warm bubble, and these little cooler bubbles off of that main flow. And then this here is, I want to say this is sea ice off of somewhere in the north, I think, in the Arctic Sea. I think even a couple of our pictures of the day for spring 2024 have also shown sea ice swirls and vortices and eddies. So kind of a cool little thing here. So that was an introduction to surface circulations. The following video will dive a little bit further into some of these other circulations, and then we'll dive into waves. So also, as I prefaced, these next several chapters, it may seem like a lot, but they're relatively short. So we're going to be working our way very quickly through them. Thank you so much for your time and attention, and I hope you enjoyed. Thank you.